and welcome to Lessons in Logic, video number 33. In this video, we're going to learn about truth tables. So we are in our unit on deductive logic, which is to say we are studying methods of testing whether it's possible for the premises of an argument to be true and the conclusion false at the same time. And we hope that it's not possible. If it's not possible, an argument is considered valid. Validity is valid is a technical term in logic, and validity is that quality of an argument such that if it's true, the conclusion if its premises are true, the conclusion has to be true. In other words, a valid argument is one in which it's not possible for the premises to be true and the conclusion false at the same time, and that's a very good thing for an argument. Now, in statement logic, we're in our unit on deductive logic, and we're in our subunit on statement logic. In statement logic, we test arguments for validity by symbolizing them and then looking at the pattern of the argument, or the way we're reasoning about things, not the things we're reasoning about, using those symbols, using the symbolic representation of an argument. And how do we symbolize it? Well, above all, we want to convert our argument's statements into symbols, and specifically the atomic statements. That means the small statements not made of any other. Okay, so here's a simple statement: the tea is hot. Here is a statement made of that statement: the tea is not hot. Actually, no, let's just say it's not the case that the tea is hot. That would be a better example. So there's the statement the tea is hot, and then there's the statement it's not true that the tea is hot. And one statement is made of the other, but not vice versa. The simplest one, the one not made of any other, that's a simple statement. Here's another complex statement made of now two statements. The tea is hot, and the water in the electric kettle is also hot. That's a statement made of two statements. Okay, so we want to symbolize, using capital letters, the atomic statements in an argument. And we also use other symbols to simplify things. And that reminds me, I didn't quite prepare my notes. There's one detail I forgot. Let's see, let me fix that right now. Okay, fixed it. I got the symbols I need. I'll just copy and paste them up here for if and when I might need them later. And I'm wondering why my computer is being kind of freezy, but there we go. It's now working. Okay, so we are in our unit on deductive logic, test for validity. We are in our subunit on statement logic, where we test arguments for validity by symbolizing them using the system where we isolate the smallest statements in an argument, the atomic statements, and we symbolize them using capital letters, and then we use other symbols for other things. Now, I really need to stop with the review in this video because I've gone over all of this so far in other videos. With that much review, which I hope is not too much, sorry if it was, let's now state, with the truth table method, you can test any argument for validity, assuming you know how to translate it into symbolic statement logic. Use capital letters to symbolize the atomic statements in the argument, and then use these other symbols to symbolize everything else in the argument, and then you're good. If you can put an argument into this form, you can test it for validity using a truth table. The truth table is the best method we have so far in the entire study of logic for testing arguments for validity, at least in that respect. It's the best method of testing arguments for validity in that it can test any argument. It has one disadvantage if we're using the generic truth table method. We'll get to that at the end of this video. Let's go. Let's do it. Let's go to truth tables. So a valid argument is one in which it's not possible for the premises to be true and the conclusion false. An invalid one is one in which it is possible. And the truth table method can test any argument for validity. And truth tables for arguments build on the simpler truth tables we built for statements. Now, we've already seen this in an earlier video. Let's make a truth table for the statement, if it's raining, then the ground is wet, using a scheme of abbreviation. So please always use a scheme of abbreviation. It increases clarity of everything so much. And when I say use a scheme of abbreviation, I mean first define the symbols you're going to use. Give a key, give a legend, give this right here. R for it is raining. G for the ground is wet. And we should probably go ahead and give it a proper symbolization. Now, we could use the arrow symbol. I actually like the arrow symbol better, but I don't happen to keep it in my notes. So we're using the horseshoe symbol, which for our purposes works just fine, except it's messing up the font, which irks me. Okay, so here is the statement, if it is raining, then the ground is wet, symbolized. The horseshoe means if then, and it goes between the if statement and the then statement. So here's an atomic statement. It is raining. We symbolize it as R. Here is an atomic statement. The ground is wet. We symbolize it as G. These are statements not made of any other statement. Rather, statements are made out of them. And the statement made out of them is if R, then G. Our horseshoe G using that symbol. So now let's make a truth table for this statement. Actually, I don't suppose we will need 3 columns. Now, what this means is that the statement, if it's raining, then the ground is wet, is true, except for when it actually is raining and the ground is not wet. And what we do in this truth table is we lay out all the possibilities that are open to this compound statement. There's the possibility where the if clause is true and the then clause is true. The R is true and the G is true. Then there's the possibility where they're both false, and there's the possibility where first one is true, the other false, and the possibility where vice versa, the other is false, and then the one is true. The one is false, one true, the other false, the other true, the one false. Okay, so these are the possibilities: true, 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 false, false, true, false, false. These are all the possible combinations of truth and falsity for the atomic statements in this statement. And that gives us these possibilities for the truth and falsity of the compound statement itself. It's true in 3 of 4 possible combinations. In other words, it's true, once again, except when the antecedent is true and the consequent false, when the if clause is true and the then clause is false. You could think of this as 4 different situations. That's a very good way of thinking of this. There is the situation where the antecedent is true, the if is true, and the consequent, the then, is also true. There's the situation where they're both false, and there's, again, the situation where the first is true, the second false, and where the second is true and the first is false. And in those 4 situations, this is where that leaves the compound proposition: true, false, true, true. Cool. So now let's formally state what I don't think I formally stated in this entire series yet. What the heck actually is a truth table? With this illustration up, we should be able to understand the definition of truth table pretty well. A truth table is a chart. And specifically, it's a chart that shows all the possible combinations of truth values for the atomic propositions in a complex statement or in an argument. Now, when I say truth values, I just mean whether it's true or false. So complex propositions, propositions made of other propositions, have parts. And the smaller parts of those propositions are the atomic propositions, the simple propositions, and those are the propositions that are not made of any other propositions, like it is raining, or the ground is wet, or the tea is hot, or Mark is tired right now. And that's why he has tea. But the proposition Mark is tired right now, and that's why he has tea, is a complex proposition made of the proposition Mark is tired and the proposition that's why he has tea. So a truth table is a chart that shows all the possible combinations of truth values for the atomic propositions in a complex statement, or in an argument which has more than one atomic proposition in it as well. Now, this definition is not all we need, but it's a good start. We'll get back to that definition in just a moment. I think things will be a little clearer then. But first, let's take this and build on it. Truth tables can be made for statements. These are easier truth tables. Let's say easier rather than simpler. They are simpler, but if I say simpler, you're going to be thinking I'm talking about simple in the technical sense. But simple in the technical sense just means a proposition that's simple, a proposition that's not made of any other propositions. Parallel to the phrasing atomic proposition. Go back and watch as many earlier videos as you need to review the vocabulary. Atomic proposition and simple proposition mean the same thing. They refer to a proposition that has no other propositions as parts. All right. So now let's build on this. And then make a truth table for a whole argument. let's build on this in order to make a truth table for a whole argument. So first, as usual, I recommend a scheme of abbreviation. And the scheme of abbreviation we just used will be fine because this argument builds off of this atomic proposition. So this atomic proposition in particular is if it's raining, then the ground is wet. And it is raining is another premise of the argument, and the conclusion is so the ground is wet. Looks to me like a good argument. So to symbolize the argument, we do this. We lay out our scheme of abbreviation. R is how we will symbolize the proposition. It's raining. G is how we'll symbolize the proposition. The ground is wet. And now to symbolize the argument, we simply fill in the details using this system. And without reviewing this particular thing in this video, once again, horseshoe is our symbol for if then. R, horseshoe G, is how we symbolize our first premise. If it's raining, then the ground is wet. Now our next premise, it is raining, is going to be symbolized with a simple R. And then our conclusion, the ground is wet, will be symbolized with a simple G. So that is how we symbolize the argument. Now a truth table for this argument will have the same number of rows because there's the same number of possible circumstances that are available to this argument. The circumstance where R and G are both true, the circumstance where they're both false, and then both versions of a situation where one's true and the other's false. So I like to do a truth table this way, and something has gone wrong with my truth table. I think it must have copied and pasted not the content into the truth table, but the oh, I don't even know what it did. Maybe it copied and pasted not the content into the truth table, but the whole. I copied and pasted a table next to a table. Never mind. Now we're making a truth table for a whole argument. So the argument is made of the atomic propositions R and G. These are the 4 different ways they can be true or false. And the argument we put here, and you'll notice there's going to be some repetition. And I think if Microsoft doesn't give me any trouble, we should be able to copy and paste. And what do you know? All Microsoft did was clean up the formatting a bit, which is fine with me. All right, so that's it. That's how you make a truth table for the argument. So let's observe what we just did. This chart has the same number of simple propositions or atomic propositions, and we chart the premises as well as the conclusion. Now, there are customs you can use for truth tables, like commas to separate the premises from one another, maybe some sort of extra thing to make it obvious which columns represent the atomic propositions the argument's made of, which columns represent the premises, which columns represent the conclusion. So if I were doing this on a whiteboard, I would use a comma and a therefore. Let me see if I can do that here. I think that'll work, but I'm going to have to pause and find a therefore symbol. I don't have it ready to Control-C, Control-V in my notes. Just a moment. And there we go. I don't like that comma custom with what I'm doing here. I don't think I want to use commas. The triangle dots here, that's a symbol for therefore. So I think I like the custom of using that to symbolize which column is the conclusion. I think maybe I'll just symbolize which are the guide columns for the atomic propositions by putting them in bold. So let's do that. What we're doing here is making a little clearer what column is for what. And we're using bolding for the guide columns for the atomic propositions. We use bolding for the guide columns on the atomic propositions. bolding on the guide columns for the atomic propositions. Then we have the premise columns, and then the conclusion column is marked with a therefore symbol. So everything in our truth table, using the conventions I'm going to be using in this video, will be a premise column, or it will be symbolized by its bolding to be a guide column for an atomic proposition, or it's going to have a therefore symbol to symbolize it's the conclusion column. So now let's go back to the definition of truth tables. A truth table is a chart showing all the possible combinations of truth values for the atomic propositions in a complex statement or an argument. That's just the definition of a truth table. Now I'm going to add to that definition an observation on why the heck we're even doing this. We're doing this because by laying out all the possible combinations of truth values for the atomic propositions in a complex statement or an argument, or specifically in an argument, we can see all the possible combinations of truth values for the premise and the conclusion, and that's how we know whether the argument is valid. In other words, an argument has that special quality that in logic class we call validity, when its premises cannot be true and its conclusion false at the same time. So we're dealing with statement logic. We're dealing with the idea that some propositions are made of other propositions, and those propositions are true or false depending on whether the propositions they're made of are true or false. And so if you can identify all the smaller propositions, the ones not made of any others, in an argument, and lay out all the possibilities for whether they're true or false, you can use that to determine under what possibilities all the other statements in the argument, like this complex proposition, if R then G, well, all the possibilities for when those statements are true or false. And then you can use that to find out whether there's any possibility where the premises are true and the conclusion false at the same time. So once we have all the different possibilities charted, since validity means it's not possible for the premises to be true and the conclusion false at the same time, we look at the chart to see if it's possible. We look at the chart to see, in other words, if there's any row, since every row describes a situation, if there's any possible situation in which the premises are true and the conclusion false at the same time. So in our first row, where R and G are both true, the conclusion's true and the premises are true. No problem there. In the second row, where R is true and G is false, the conclusion is false, but one of the premises is also false. So no problem there, as we say in Hong Kong, momentai. In the third row, where R is false and G is true, again, as we say in Pakistan, koi baat nahi, no problem. The conclusion is true. One premise is false, it doesn't matter. We're looking for whether the premises can be true and the conclusion false at the same time. And then final row, where R and G are both false. Once again, no problem. The conclusion is false. So we don't have the conclusion is false, but one of the premises is also false. So no problem. We do not have true premises and a false conclusion. There is no possible way, in any possible circumstance, in any possible world, where the premises can be true, the conclusion false at the same time. That makes this a valid argument. So we did it. We showed that the argument is valid. Now, if you're doing a homework assignment, you should probably say this. Really do not ever forget to say that the argument is valid. Never forget to include that, unless your teacher actually doesn't need you to or wants you not to. I don't know. I can't imagine why. But normally, at least in a homework assignment, if you're making a truth table for an argument, if you're making a truth table for a proposition, that's different. But if you're making a truth table for an argument, your job is to show that whether the argument is valid. So say that. But also, if unless your teacher just has really simple instructions, you might want to say why, and it is likely to be a useful exercise to say why. Why is it valid? It's valid because there's no row on the argument, no row on the truth table where the premises are true and the conclusion false at the same time, which means there's no possible situation in which the premises of the argument could be true and its conclusion false at the same time, and that's That's what truth tables are for arguments. That's how we use them. The rest, I think the rest is just practice. So let's do the practice, and maybe let's do it a little more quickly. I wanted to look at this argument. If it's raining, then the ground is wet. It's not raining, so the ground is not wet. And remember, it's not raining is itself a complex proposition. That's one of those rookie mistakes to avoid. I've done it myself. I confess it. Thinking that a not proposition, a negation, a denial is an atomic proposition because it's only made of one proposition. Well, it's still made of a proposition that's not identical to itself. So at the moment, it is raining. I'm happy to report because I like rain. It's raining rather hard. It's raining beautifully, and the ground, I'm sure, is very wet out there. So the statement "it is raining" is a proposition, and the statement "it's not raining" is a denial of that proposition, a negation of that proposition. So it's made of that other proposition. So it's considered a compound proposition. A compound proposition is not a proposition made of two or more other propositions. It's a proposition made of any proposition other than itself. So a negation is not an atomic proposition. Now we're going to need our symbols here. Which symbols are we going to need? We're going to need the tilde and the horseshoe. Oh, and the therefore. So what we want to do is test this argument for validity. We'll borrow those symbols in a moment. And as usual, I recommend a good scheme of abbreviation. R for it is raining, again, will work just fine. And G for the ground is wet. And those are the only symbols we'll need for the atomic propositions, because those are the only atomic propositions. Now, let's symbolize the argument. If R, then G is what I want to type, and before I even finish typing, I realized, no, I can't do that. I'm symbolizing the argument. So first, I want to number my statements, and second, I want to use a horseshoe. R horseshoe G means if R, then G. If it's raining, then the ground is wet. That's how we symbolize that statement. Now, our next premise is going to be not R. So this symbol is a tilde. Tilde means not. Tilde means it's not the case that. And so the argument is, if it's raining, then the ground is wet, or R horseshoe G. If R, then G. It's not raining, tilde R, so the ground is not wet, tilde G. Now, we still have just 4 atomic propositions. So the beginning of our truth table is going to look exactly the same. And let's bold our columns for the atomic propositions. So now we've already laid out all the possible ways R and G could be true or false. Both true, both false, one false, and the other true, or vice versa. So now we symbolize, now we write in our columns the symbols for the rest of the argument. And those are the arguments, premise R horseshoe G, its premise tilde R, and its premise, its conclusion tilde G. So there we go. This is a beautiful truth table. Now, R horseshoe G is true except when, if you have any issues here, go back and review the video that went over this. Off the top of my head, maybe 2 videos back. Ask a comment in the comment box if you don't know and need to know. R horseshoe G is true except when R is true and G is false. In other words, it's true that if it's raining, then the ground is wet, except for a situation when it's raining and the ground is not wet. If it's not raining at all, it's true that if it's raining, then the ground is wet, etc., etc. Okay, so that's our first premise. Now, this premise, this is going to be very simple. Tilde R is going to be the exact opposite of R. right? It's a denial of R. When it's true that it's raining, it's going to be false that it's not raining. When it's false that it's raining, it's going to be true that it's not raining. Similarly, for tilde G, it's going to be the exact opposite of G. When the ground is wet, it's going to be false that the ground is not wet. And when the ground is not wet, it's true that the ground is not wet. So those are the premises of our argument. Now, look to see if there's any possibility where the premises are true and the conclusion false. Look for a line on the truth table. Look for a row. Look for a possible situation in which the premises are true and the conclusion false. And then if you're doing your homework, if you're preparing for a test and you're going to do something like this on the test tomorrow morning, oh, I hope you're not procrastinating and studying late. But if you are, or if you do a test at another time, you'll want to indicate which column. It's usually good to do that. I think I was taught to circle it. I recommend circling it. Highlight it in yellow. I've known arrows to be drawn pointing to it. Really, any way of indicating which column, which row you're talking about is totally fine. Sometimes I've seen, I think, just circling this to highlight that this is the situation where this is the scenario, this is the possible world in which the premises are true, the conclusion false. That's a good exercise. I almost want to recommend that, but I think it's probably easier for most of us to just circle as a default setting unless something else works for you or you have a teacher who has different requirements. Circle the whole row that has true premises and a false conclusion to point out this is the truth table evidence that the argument is invalid. And keep in mind that what that means is this, when you circle the whole row, what you really mean is that this situation where R is false and G is true is the kind of situation in which the premises will be true and the conclusion false at the same time. So to complete our work, we don't want to neglect to state that the argument is valid, and if your teacher requires you to, or as a useful exercise, just to make sure you understand things, state why. So I can circle this with my zoom control functions. Here, I can use my zoom annotation powers to circle this row. But I don't know how to circle it in Microsoft Word, so I'm going to have to remove that circling in a moment after I finish this. Okay, so it's invalid. It's invalid because there is one row where the premises are true and the conclusion false, meaning that there is a possible situation in which the premises of the argument could be true and its conclusion false at the same time. And you should probably state when you're doing this which row that is. There you go. That's how you test an argument for validity using a truth table. Oh, let's make that circling go away. Now, let's do this one. This one should be fun. Let's chart a famous form. This is, let me read this. Either the soul is immortal or it's not. If it is, then death is the gateway to another life. If it's not, then death is the end of sensation. Therefore, either death is the gateway to another life or death is the end of sensation. Okay, this will be fun. This is Socrates' argument in Plato's Apology, or at least part of it. So first, as always, make a scheme of abbreviation. Any capital letter will do as long as you don't get confused. I'm going to do I, or the soul is immortal. That's one of our atomic propositions in the argument. G, for death is the gateway to another life. E, for death is the end of sensation. Oh, good, that's it. Those are only atomic propositions. Either the soul is immortal or it's not. If it is, then death is the gateway to another life. If it's not, then death is the end of sensation. Therefore, either it's the gateway to another life or death is the end of sensation. Good. I thought we were going to have 4, but we don't because there's only one atomic proposition in our first premise. So now, to symbolize the argument with the scheme of abbreviation, X would be better when I'm just setting up blanks to fill in. I instinctively type D for some reason. All right. So now, symbolizing this argument using our scheme of abbreviation here, either the soul is immortal or it's not is our first premise. And we can symbolize that as either I or not I. And I'm gonna do this step first, and then I'll work in the proper symbols. Either I or not I. If it is immortal, then death is the gateway to another life. If it's not immortal, then death is the end of sensation. So if I, then G. If not I, then E. Therefore, either death is the gateway to another life or it's the end of sensation. Either G or E. So the symbols we're going to want for this argument are the therefore symbol, the horseshoe symbol, and the or symbol for the wedge symbol. Oh, and a tilde again. So let's just copy those over here where we'll need them, and then make our no wait, we have to fill the argument first, obviously. Okay, so either I or not I. So the wedge, which is actually just a V, I didn't really need to copy and paste it. The wedge means or, a lowercase v though. And the tilde means not. So now we've symbolized our first premise. I wedge tilde I means either I or not I. Either the soul is immortal or it's not. And if it is immortal, then G. That's another horseshoe. If I, then G means I, horseshoe G. If the soul is immortal, then death is the gateway to another life. And it looks like we're going to have another horseshoe here. And we need to work in a tilde here. Tilde I, horseshoe E means if not I, then E. If the soul is not immortal, then death is the end of sensation. So either G or E, which means G wedge E. G wedge E means either G or E, either death is the gateway to another life or death is the end of sensation. Yeah. From time to time, some system in this building makes that noise. I have no idea why. I don't think it's affected by whether there's an air conditioner on or off. It's a minor distraction. Just this one time, it totally froze my brain. Okay, so let's keep the therefore symbol. We'll need that in a moment. Okay, so note how what we have here is a very simple argument from a very, well, I won't say a very simple philosopher, but in some respects, Socrates is a very simple guy. At any rate, he's giving an ordinary argument that pretty much anyone can understand. He's not doing anything fancy. He's not, he's not talking like a logic nerd in a logic class. He's just a pretty much ordinary guy, not particularly rich, only famous because he has weird ideas and questions authority. He's weirdo, spends his days walking around Athens talking to people. Socrates, the weirdo, gives this argument. And in context, it's about why he's not afraid of death. And as long as we do what is right, we don't need to be afraid of death, he says, et cetera, et cetera. A very important reflection on the meaning of life. We might have our issues with the argument. We might doubt one of the premises. There may be religious questions here. But anyway, this is Socrates' argument. And it's a very simple, straightforward argument given in pretty ordinary language in Plato's Apology, with very practical consequences about not being afraid of death, right? But if you can just symbolize it, you can test it for validity using a really good system for testing arguments for validity. Most of the work comes in the symbolizing of it. We're just going to go through the motions for the testing of validity. It's going to be very simple. Okay, what's my point here? My point is, actually, I think my main point is just this. If you look at these symbols, this symbolized argument, and you think, oh my gosh, I don't know what I'm looking at. Why am I looking at these weird symbols? And if you, like many of us, find some straightforward, ordinary language remarks on the meaning of life to be much easier to comprehend than all these symbols? Well, one, you might find the symbols more easy to work with some more practice, and you can review the introduction of these symbols in earlier videos, etc., etc. But two, try not to be confused. All we're doing is symbolizing this argument. There's steps to what we're doing here. We take this argument, we find ways, we use this way. All we have to find is which abbreviations are we going to use. We use this way to symbolize the argument with capital letter abbreviations for its atomic statements, and then we represent the argument symbolically. Then our final step is to test the argument for validity using those symbols. But these symbols that seem weird, they mean precisely this, at least in conjunction with our scheme of abbreviation here. They mean the same thing. Here, I'll color code it and bold some stuff. What's in bold and red means exactly 100% totally the same as what's italicized in blue, okay? Try not to lose sight of that if that's any difficulty. Okay, but once we do get the symbols, we want to test the argument for validity without looking at anything else. Now, how many simple statements, how many atomic statements do we have? We now have 3. So how many lines in our truth table? The number of rows in a truth table is 2 to the power of the number of simple propositions in the argument. So I think we're going to need 8 rows plus 1 guide row. Now, how many columns will we need? 3 guide columns, and then 1, 2, 3, 4, 3 premises, 1 conclusion. So I'm going to insert. This will be a little easier if I just start again. I'm going to want a 9-row table, and I want 7. I want 7 columns. Now, as you may recall, I like to indicate which are the guide rows for the atomic propositions, which are the rows laying out these are the possible scenarios that are open to this argument. I want to bold those, and our different atomic propositions are I, E, and G. And then we're going to have 1 row for each premise. And 1 row for the conclusion, and we mark out the conclusion row with the therefore symbol, which, of course, I've already lost track of. And there we go. Now, I suppose I'd better do 3 things. 1, I better say something about how to set up the guide columns. 2, I better do this argument in a slightly abbreviated way. Then I'd better add some more columns and show how you can do this with a little more detail if you need to. All right, so I keep thinking that my notes are going to tell me when to tell you what I'm about to tell you. And I don't think it's actually going to be in the notes, but I really should tell you explicitly. So let me just type this up here. The columns to the far left of the truth table we call the guide columns. These are the columns these are the columns that lay out, columns. These are the columns that lay out all the possibilities for truth and falsity for the atomic propositions in the argument. The number of atomic or simple propositions in an argument is the same as the number of guide columns in the truth table for the argument. The number of rows is 2 to the power of the number of simple propositions in the argument. So if you have 2 simple propositions, there'll be 4 rows. And if you have 3 simple propositions, there'll be 8 rows, etc., etc. And sorry, for the first column, your first half of the row should get a T and the next half a false, like so. For the last guide column, you should alternate between T and F, like so. For the columns in between, you follow the pattern. Now, I think I'll make one effort to state this more formally, but I don't think you need me to. I think you can see what the pattern is. Just looking at this, you can see what the pattern is. We have 8 rows to fill in with T's and F's. We make half of them T's and half of them F's in the far left column. And in the far right of the guide columns, we alternate TF, TF. So it's 4 T's, then 4 F's, and then 1 T, 1 F, 1 T, 1 F in the third column. So what's happening in the second column? What else but 2 T's, 2 F's, and repeat. That's the pattern. I don't think I need to explain it, but let me see if I can find the words to explain it clearly. Where was I typing all this? I'm annoyed by the formatting. I'm getting distracted by it. Okay. I don't know how else to say this except using a lot of extra words. So ignore this and just follow the pattern if you understand how to follow the pattern. But for the second guide column's first half, give, no, that's not right. For the first guide columns, first half, I mean, the first bunch of truths, I can just say that. For the first guide columns, T's, give half that many T's in the next column, followed by the same number of F's. Then for the first guide columns, falses, give half that many T's in the next column and the same number of F's. Or just follow the pattern. I don't want any unnecessary rookie mistakes. I've seen them a lot. But it's very difficult to find words that won't be so precise that the sentence is just going to confuse all of us. And my brain is half frozen just trying to say it. Worn out, half worn out. But basically, here's what we're doing. Take the first half of your row, let's give them t's in the first half, and then f's in the next half. For the next column, for the first half of those rows, divide it in half and make t's there. And in the next one, divide it in half and make t's there. And false is where you don't have t's. And then for each bunch of t's in the following column, divide it in half with t's and f's, which gives you this. And repeat for the f's. And this is how we lay out systematically all the possible combinations of truth values. All right, enough of this. Let's fill in the argument. Okay, so let's do a simple one. I wedge tilde I. Either I or not I. Either the soul is immortal or it's not. Well, that's very simple. That's always going to be true. No problem there. Wedge, G wedge E, either G or E. Let's fill in this. This will be simple as well. For every G that's true, G or E is going to be true. And it's going to be true there. And then it's also going to be true when E is true, whether or not G is true. So E is true here and here. So we want T's here. So we add T's there and there. Now let's double check. E wedge G. Is E wedge G false here and here? Yes, because E and G are both false. So our premises are our conclusion is only going to be false on these two rows. So the argument's going to be valid unless we find T's in all of these boxes. Will we? Well, let's find out. I horseshoe G. Now, building on what we covered in earlier videos, I horseshoe G is going to be true except when G is false and I is true. So in these four rows where I is false, I wedge G is going to be true. So what are we looking at? I horseshoe G, not I wedge G, sorry. I G. Okay, so it looks like we're going to have a TF-TF. I horseshoe G is true except when I is true and G is false. Let's do it horizontally for a change. When I is true and G is true, if I then G is true. When I is true and G is false, if I then G is false. When I is true and G is true, once again G is true, and once again when I is true and G is false, if I then G is false. Tilde I horseshoe E. Well, now's the part where I'm just going to fill it in briefly. I won't even tell you how I get here, maybe. You can figure this out slowly, but in a moment I think I'll show you how to do it in more detail if you need to. Tilde I horseshoe E. Let's see. Tilde I. Basically, I want a truth value to be true. There we go. So that's the truth table. If you don't know how I filled in this, wait a bit. I should get to it. All right. So now we test the argument for validity using this truth table. Is there any row where the premises are true and the conclusion false at the same time? What fun. There's not. The premises are true. When the premises are true, the conclusion is true. The premises are true. All the premises are true here. And in all these situations, the conclusion is true. And here where the conclusion is false, there's at least one false premise, so no problem. So now we can just, I think we can just copy and paste our first statement of validity. So finishing the work of explaining why the argument is valid, that. And we're basically done with this argument, but I need to go into a little more detail to explain things. So let me say something about different ways of making truth tables. A textbook or a particular teacher with her or his own preferences might make tables in different ways. your teacher or your textbook might have you making tables for an argument form, but not for a specific argument, using lowercase letters instead of uppercase letters. I think that's fine. If you don't know what I'm talking about, this video has gone on long enough, so go back and review the previous video that talks about it. Don't know which video that is. I'm not sure I do off the top of my head, but you're welcome to ask. Maybe I can figure it out. It's not more than 3 videos back. Maybe it's only 1 video back, maybe 2, I don't know. A counterexample on which, rewind to the intro unit, I don't know, video 12, I think it was. A counterexample is an argument with true premises and a false conclusion using the same argument pattern as the argument you're refuting. In other words, a counterexample shows that an argument uses a bad pattern of reasoning by, or at least an invalid pattern of reasoning, which is not necessarily bad, but go back to the intro unit or wait till the next unit on inductive logic on that. Let's see, what was I saying? A counterexample is an argument. A counterexample shows that an argument pattern is invalid by giving us a new argument using the same pattern with premises that are true and a conclusion that's false. A truth table shows us under what conditions the atomic or simple propositions of an invalid argument will produce all true premises and a false conclusion. In other words, a counterexample is an argument which would be charted on a row of a truth table with all true premises and a false conclusion. And any row on a truth table with all true premises and a false conclusion describes various possible counterexamples. In other words, that video on counterexamples back in the intro unit is telling us what sort of things we should look for, actually not here, but on an invalid argument here. That video on counterexamples in the intro unit is telling us about this kind of situation where the premises of an argument are true and its conclusion false at the same time. But this is not what I wanted to be talking about. I just keep finding these notes and finding myself talking about them. Okay, let's save this remark for the end. So let's get back to where I was saying something about different ways of doing truth tables and explaining how the heck I filled this in so quickly. Some of you understood this perfectly. Some of you are like, what the heck did he do? I can't even figure this out. Like, I basically understand what these symbols mean. Or maybe some of you are having trouble even understanding what the symbols mean. But even if you do understand what the symbols mean, maybe you're thinking, oh my gosh, I can't fill in all that kind of detail. I basically maybe understand why tilde I horseshoe E is true in this scenario, but it took me a long time to get that. I can't do all of this without 20 minutes. Well, you're in luck. There's another way of doing this, but it's not a huge pile of luck because there's still some work that may go into this. Let me, it might be easier to just use Microsoft Excel for something like this, but now let me try it in a different way. I'm going to try it right here in Word. I'm going to try with more columns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Here's another way you can do truth tables, and it might be a lot easier to use Microsoft Excel. I think I needed 18. I think I've got 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I need 7 more. And how many rows? I think I only need 1 more row. So here is how you can make a truth table where it's a little easier to do some of these more complex calculations. Just give 1 column for each symbol. So that's going to be hard to do. I better just copy and paste. No, not copy and paste. type one at a time. Wait a minute, something's amiss. I wedge tilde I, good. I horseshoe G, good. I left out a, I didn't put the tilde there where I was supposed to. Tilde I horseshoe E, there, that should be right. And then therefore symbol G wedge E. Now, why did I think I was going to have all that many rows? And now I'm not finding that many rows. Well, let's check. All right, not rows, columns. The more complex, slower, but also a whole lot safer way of doing truth tables, and this will actually help you avoid a lot of mistakes, probably. It's a very good exercise for anyone studying logic, actually, including me, is to make truth tables where you have a column for every dang symbol you've got. And here actually is where you really would want to add some comma columns, which I might do in a moment. But let me make sure I've got everything copied properly. A wedge tilde I, then I horseshoe G. So far, so good. Tilde I horseshoe E, good. And then therefore G wedge E, good. We're good. We're good. This is going to work. So now add columns separating premises. Except now that I think of it, I don't want columns separating the premises. I think that's ugly. Instead, I'm going to do something else to make it obvious. It turns out, contrary to my confusion, we don't need this many columns. So here's something else we're going to do to make it obvious which is the premise column. And which is another premise column, and which is another premise column, and which areas are dealing with the premise and which are not. And now I'm really starting to wish I was using Microsoft Excel. I wanted to put some borders around these columns, but apparently I don't know how to do that in Microsoft Word. Wait, oh, there it is. There's the borders button. Okay, this should work then. Oh, that didn't work at all. I better pause this recording while I figure out how to use my computer. And I don't think I can even do it in Microsoft Word. I just don't have as many options as I do in Excel. So here's our well, I seem to be having some slight difficulty zooming in just the right amount. Maybe I'll make myself smaller. That's a good plan. Okay, so here is our argument. It appears they have all the right premises and everything. And what I've done is I've emphasized which columns are dealing with one particular premise or one particular conclusion. Let me just check and see if I could make the outside borders extra thick. I don't think that's going to do it. Nope. I don't think there's anything I can do to make the outside borders extra thick. Yep. That seems to be all I can do. Okay, so I hope it's clear enough. In this little exercise, what we're doing is we're making a truth table like we did before, but we're giving one column for every symbol in the argument. We won't fill in the therefore column. And we are everything should be centered. I feel better that way, I think. We are giving one column for every symbol in the argument, and we're going to fill in truth values for all of them except for the therefore. And the ones we're really going to have to care about are going to be the columns for the premises here and for the conclusion there. And then, of course, we'll care about any particular row where we might have true premises and a false conclusion, although I think we already established that's not going to happen. So what we did before is we just went straight into filling in these rows, but you might have noticed on this particular premise, it was a little harder to see how to do that. What I want to emphasize is how you can do that more easily. That's why we're doing this exercise. So it's not actually easy in the sense that you have to do a lot more writing, and it's going to be very difficult to do it without Microsoft Excel or printed graph paper, which is, the old school way of doing it, which is probably what Dr. Mark Sadler had me doing in my first logic class. I think we used graph paper. It was awesome. Graph paper is a great way of doing truth tables. Okay, so these are the columns we want to fill in, and it's all we filled in before. But in order to go into more detail and know what goes in these columns, we're going to fill in other stuff. And you want to make sure these are the ones you looked at. You look at in the end. I bolded them. Now I'm trying to ask myself, should I do something else to make this a little easier for some of us? Should I color code them? Or should I just color code which premises we're interested in? Color code. I think I'll color code this because these thick borders, they're not thick enough to make me quite happy. Oh, wait, you know what I could do? Hang on. Of course, I just need to make the lines, all the other lines a little less emphasized, and then the thicker bordering is good, is more visible. All the same, I think I would like to color code these and make, we'll make the first premise red, we'll make the next premise blue. We'll make the next premise green. We'll make the conclusion orange, brown, some sort of orange, maybe brown. It looks brownish to me, but maybe it was labeled orange. Anyway, this is how you can fill in a much more detailed truth table. Just don't get confused. Remember, once you've laid out all the details, you only need to look at just the right columns. The main premise columns and the main conclusion column are these. They're the ones I have bolded, and they're the ones that represent the truth value for the whole statement. The truth value of I is going to be in the first row true, and the truth value of tilde I is going to be in the first row false. The truth value of one or the other is going to be true. This is the truth value for this entire statement, okay? So now, filling in the gaps. Where you have the atomic propositions, you could just copy what's in your guide columns, these atomic proposition rows. Which I will finish doing momentarily. And are we done? I think we're done. So now you just fill in the other rows based on what you have there. Start wherever you like. You look at all these symbols and your brain's like, I can't do it, it's too much. Then my advice, start somewhere, preferably somewhere simple. Just start somewhere, preferably somewhere simple. You're not ready for these main columns yet until you've figured out everything they operate on. Remember, these main columns are, well, these are symbols, and they operate on specific things. This wedge operates on the statements to its immediate left and its immediate right. You've already got that filled in. So you can do this one. And it's going to be true, except for when both of the things on both sides of it are false. This one you're not ready to fill in because it's going to operate on this column. And this one you're not ready to fill in because it's going to operate on this column. Well, on these two columns to its immediate left and its immediate right. This one operates on, two statements to its immediate left and its immediate right, which means these columns. This one you're ready to fill in. It's true except when the if is true and the then is false. I horseshoe G means if horseshoe then G, and it's true except when I horseshoe G means if I then G, which is true except when I is true and G is false. So there we go. Now the tilde i's might have been a better place to start. We were ready to start there, and it's very simple. It's just the opposite of whatever the I is. Where I is true, tilde I is false, and vice versa. So now this wedge here is going to be true unless both disjuncts are false. The statements do its right and left. But as we already saw, I wedge tilde I, either a statement is true or its negation is true, always true. Now this one, what do we got? This is going to be true except when its antecedent tilde I is true and its consequent false. So I'm just going to glance over here and observe that these 4 boxes have a true consequent, so no problem there. It's going to be true. Well, not there. Those 4 boxes. So with these 4 boxes, consequent is false. So everything depends on whether the antecedent is true. The antecedent is false on these 2 rows, so no problem here. Here, though, the antecedent is true and the consequent false, making this one false. And now you look to see whether in these specific rows, these specific columns, it's possible to have true premises and a false conclusion, and we already know the answer. The only situations where you even have a false conclusion are these here rows 5 and 9, and in each of them you've got at least one false premise. Darn it, I lose my highlighting when I try to annotate. At least one false premise here for this row and here for that row. So there you go. That's how you do a truth table with more detail. Now, finally, that's a beautiful truth table. I love it. Now, finally, you'll note that that was 8 rows. What if we had one more atomic statement? This thing would have been twice as big. It would have gone down all the way to here. Wait, 1, 2, 3, 4, 5, 6, 7, 8. It would have gone 1, 2, 3, 4, 5, 6, 7, 8. It would have gone all the way down to here. And if we had 5 atomic propositions, it would have been double that. So all the way down to, I don't know, 32, 33, row 33 here. It would have been that long. We have our guide row up here, and then we have 2 to the power of x, where x is the number of atomic propositions. So it would have gone pretty far if we had 5 atomic propositions. What if you had 6 atomic propositions? After a while, it gets almost impossible to fill it out without a spreadsheet or for graph paper, and maybe next to impossible with them. In theory, you can test any argument for validity. So I think I had the sense to say in theory earlier when I said you can test any argument for validity using this method if you can just put it into symbolic statement logic. Well, that's only true in theory, because with the number of atomic propositions growing, you get a growing truth table, and it's growing exponentially in size. So there needs to be a way of doing this method in an abbreviated fashion. That's what we call the abbreviated truth table method. We are going to get to it later. I think it's not the next video, but maybe the next one after that. In the next video, I think we're going to do more practice with this. Speaking of videos, this one has gone on way too long. See you next time. If you actually watched this far, awesome. You win. I don't know what you win, but good job. And see you next time.